and show you the problem if I find it again. So here it is. So we're given a graph and we're asked what makes an x value a critical value. So explain what they mean so we understand what we're trying to do here. Okay, so I printed out that graph as wide as possible, as I zoomed in as much as I could. So now let's analyze these points from x sub 1 to x sub 10. So x sub 1, is x sub 1 a critical number? Remember critical numbers, one more time, I'm going to write them here. Critical numbers come from f prime of x being 0 or f prime of x being undefined, meaning no derivative. Function exists. Anyone remembers which points of a continuous function does not have a derivative? Do we remember which points? So maybe we should refresh our memory on that. So not differentiable, but continuous. Anyone remembers that?
Corners.
Yes.
Right.
Corner. Very good. This is one. So here, f prime of x is undefined, and the function exists, it's continuous. Okay, good. Awesome. The other one. But this is not continuous, so I shouldn't even mention it. Removable. Discontinuity. Okay. The other one is a cusp. Cusp. Here, again, f prime of x is undefined. The function is continuous. And the last one is a vertical tangent. How does the vertical tangent look like? I'm going to graph it here on the side. Something like this. This is a vertical tangent. Even here, even this one is a vertical tangent. Okay, so now let's go back to our graph. X sub 1, is this a critical number? Is this a critical number?
Yeah.
Yes. Because the derivative is? What is the slope of the? Exactly. The slope of the tangent line is 0. So critical number. I'm going to jump over. Is this a critical number? I'll come back to all of them. Is this a critical number? 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 Are they all critical numbers?
Yes.
Yes.
Which type? This or this? I know it's silly, but I want to hear you say it.
0.
Yes. I'm going to call this number 1, so I'm going to call this 1 and 1 and 1 and 1 and 1 and 1. Done. Now let's analyze the other ones. Is this a critical number?
No.
No.
No, because the slope is not 0, and there is no cusp, corner, or vertical tangent. Awesome. Is this a critical number?
No.
No, because the slope is not 0, and it's not a corner, cusp, or vertical tangent. Awesome. Now, let's talk about this one. Is this a critical number?
Yeah.
Yes. Of course, not of type 1, but of type 2. Cusp. What about this one? Is this a critical number?
Yeah.
Yes, of type 2. Because it's a vertical tangent if you want, or cusp. Yes, correct. Very good. Now, question. Is this it's a critical number, but is it a max or a min?
Min.
Of course. Like this one, like this one. What about these three? They're critical numbers. Max or min?
Max.
Max, of course. What about this one? We know it's a critical number. Is it a max or a min?
Min.
Of course. We know that this one is a critical number. The derivative doesn't exist, but it doesn't mean that the function doesn't have a max or a min. Is it a max or a min?
Max.
Exactly. So this is a min, this is a max, and these are max, 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 min, min, min. Awesome. So that's how we know when the function has a derivative that is 0 or undefined. That's when we know the function has a max or a min. But because the derivative changes sign. How do I know? Very easy. Look at this. The slope of the tangent line is negative, which means the derivative is negative. The slope of the tangent line is positive, which means the derivative is positive. So it's negative, positive. That's why this is a minimum. The slope here of the tangent line is positive. Here is negative. It means the function is increasing and then decreasing. Positive slope, negative slope. That's why this is a max. Okay, enough of this. Any questions? Sorry, I know I talk too much. Sorry. So I'd like to look at a word I'm just so interested in you getting this idea. So let's look at a word problem. So this is my page 6. So we move on to 7. Okay, so let's look at a word problem and then move on. You can say move on. The time is almost over. Okay. So solar eclipse. On July the 2nd, 2019, a total solar eclipse was observable over the South Pacific Ocean and parts of South America. Fine. The path of the eclipse is modeled by. So they're giving us f of t, which is 0.00259 t squared minus, get used to these weird numbers, 0.57 t plus 36.237. Fine. F is the latitude in degrees, so in degrees. Very good. South of the equator, and t minutes after the start of the total eclipse. So t in minutes. And this is problem 71. Okay. What is the latitude closest to the equator in degrees at which the total eclipse was visible? Closest. What does the closest mean? When we say closest, we mean min or max? That's all I'm asking. When we say closest, we mean min or max?
Min.
Of course. So we expect to get a minimum. Good. So let's find the derivative as we know. Weird, but these are the numbers. We have to work with them. So 8 and 1, 10, 1, 4, 5, 0, 0, 0. T minus 0.457. So this is number 1. Of course, number 2. We want f prime of t equals 0 or undefined. Well, it's not possible. It's a polynomial function. I said this equal to 0. 0.00518 t minus 457 equals 0. I move this and divide by this. So t equals 0.457 over 0.00518. Since just a number, I'm going to do this. 0.00518. And I got 88.22. So t equals 88.22 minutes. Okay, in step number 3, I present my table from 0. Okay, it cannot be infinity, but you know what I mean. I have my f prime of t, and I have my f of t. Good. So I know you're going to say put 0 here. All I need to do is find the sign. In f prime of t, which is this, I would plug in 0, and I get a negative number. I would plug in 100 or 1,000, and I get a positive number. In the function, I have to plug in 88.22, which is not a pleasant situation, but I have to do it. Okay, so I have 0.00259 times 88.22 squared, and then minus 0.5457 times, again, 88.22. Finally, plus 36.237. And enter. So it's 16.08. I'm asking you now, what type of point is 88.22 comma 16.08? Based on what you see here. And the answer is yes, a local minimum or relative minimum, whatever you want to say, as expected. They were telling us from the very beginning, find the closest. So this is it. Nothing, no deviation from this. If you go to the left, it's not going to be the minimum. If you go to the right of 88.22, it's not going to be the minimum. This is the minimum. Okay. Now, I know I only have about 7 minutes, but I have to continue. So let's take a look at 3.2. We know that f prime gives a lot of information, increasing, decreasing intervals. It gives max, min. It gives, of course, critical numbers that are related to this. Critical numbers. But what about the second derivative? And no, we're not going to go beyond the second derivative. What will the second derivative give us? The second derivative will give us something called concavity. What is this? I'll explain in a minute. And also gives points of inflection. This one was giving us points of max, min, and increasing, decreasing intervals. This one gives us points of inflection. Let me explain what they mean. So let's take a look at our function, that same example that we had before. You clearly told me that this is a relative max, and you said that this is a relative min. Now, where does the second derivative fit here? Here it is. Notice what happens. The function is opening down till a certain point. When it starts opening up, so when the function opens up, we say it's concave up or upward. Concave upward what I like to say is that holds water. That's how my grandma taught me about concavity. She says, well, what do you know? It just holds water. Okay. You don't have to say that, of course. And the function opens downward or concave downward. It doesn't hold water. When it changes concavity, it has a point of inflection. Of course, if the function exists there and so on and so forth. So this is a point of inflection, either when the function changes from opening down to opening up, or from opening up to opening down. This is called an IP inflection point. Now, with this information, we will be able to graph. But first of all, I'd like to look at an example on how to determine the points of inflection and concavity. I can't, let me turn the page here so I can get directly to the page number that I'm interested in. My book was still open on, so we are on page 291. Okay. So 291, 291. Okay. So let's look at just one quick graph before we try to start a function. So see, it opens up, it opens up, it opens up, it opens up. Right here, it starts opening down, opening down, opening down, down, down. Oh, right here, turns again, goes up, up, up. So it opens up. It holds water. It doesn't. So between negative, whatever, I'm going to say -4 for now. It's not. It goes forever. From negative infinity to -1, the function holds water. From -1 to +1, the function does not. It's concave downward. And then from 1 to infinity, again, the function is concave upward. What happens here? Concave down, concave down, concave down. Yes, but then upward, 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 and then downward, downward, downward. So this is another inflection point, and this is another inflection point. So the inflection point here is at -1, 1. Another one is at 1, 1. So allow me just to start this. A function like, let's say 13. We'll continue it probably on Tuesday, but let's start it. So 13. So we have h of x equals x to the third minus 27x. Okay. So we want to find everything. Eventually, we're going to get to graphing. So, of course, I need the first derivative. I know I will stop in 1 minute. So whatever we can accomplish. Can anyone quickly give us the first derivative and the second derivative?
3x squared minus 27.
And the second derivative?
6x.
That's it. Of course, I have to find the critical numbers. There are no critical numbers coming from undefined. So I have 3x squared minus 27 equals 0. Of course, I will divide by 3 because I'm solving an equation. I'm allowed to do that. Not in the function, but in an equation, yes. So I have x squared minus 9 equals 0. Can anyone quickly give us the solutions for x squared minus 9 equals 0? That's why I always simplify to make it easier. Anyone?
3 and -3.
Thank you very much. And we're going to continue next time. Of course, I have to get my table going. And here's how the table will look like. I have h prime of x. I have h of x as we had before. No change there. I'm adding the last row as the second derivative. You will tell me that the domain is all in numbers. I will put in -3. 0 has to be in the table. 3. And 0, 0. We have time to finish just the derivative? Yes. So when I plug in -10, this will be positive. When I plug in 0, this will be negative. When I plug in 100, this will be positive. Now I have to go to the function and plug these values in. But at this point, you can already tell me -3, comma this will be what type of point?
Min. Oh, max.
Perfect. Awesome. And 3, comma this will be what type of point?
Min.
That's it.
Min.
Yes. So this will be a relative max, and this will be a relative min. I have to stop. I'm sorry that we didn't finish, but we're going to start from here on Tuesday. Thank you very